Welcome to the deep dive. Today, we're plunging into a really fundamental concept in stats and probability, random variables.
Yeah, fundamental is the right word.
Right. And look, statistics, it can sometimes feel a bit intimidating, can't it? But our mission here, like always, is to give you that shortcut.
Exactly. We're taking the key ideas, the really important bits from our source material.
So you understand not just what these things are, but crucially, why they matter. This deep dive, it's really tailored for you. We're aiming for those kind of aha moments, without the usual info overload.
And the source material we're looking at today, it's actually from a video for engineering and BSc students. So it's maybe a step above the absolute basics.
Which is why we're here. Our job is to make these maybe slightly more advanced ideas feel clear, accessible. It doesn't matter what your background is.
Yeah, we respect your time. We're zeroing in on the core distinctions, what they really mean in practice.
Okay, so the big question we're tackling today is basically this. How do we sort and understand data when it changes, when it varies, and why do the ways we categorize it make such a huge difference in how we measure and see the world?
And that leads us straight to the two main players, discrete and continuous random variables.
Let's start there then. Discrete random variables, what are we talking about?
Okay, so a discrete random variable, think of it simply as a variable whose value can only be one of a specific countable set of numbers.
Countable, like things you can literally count on your fingers, almost whole numbers.
Pretty much, yeah. Distinct values, you can list them out.
Okay, give us a super simple example just to lock that in.
The absolute classic is flipping a coin. Toss it once. Your sample space, the possible outcomes, just head, tail, simple.
Right.
Toss it twice. Now you've got HHHTTHTT, still countable outcomes.
Okay.
And then we could define a variable, let's call it X, is maybe the number of heads you get. So X could be 0, 1, or 2.
Ah, okay, so X can only be 0, 1, or 2, nothing in between.
Exactly. And then we can talk about the probability of each of the probability distribution.
And this is where, for me at least, the aha moment comes for discrete variables. If you were to graph this, say, number of heads on the bottom axis, probability going up, you'd only have actual data, actual probabilities at the point 0, 1, and 2.
That's right. Specific, separate points.
But if you tried to ask, what's the probability of getting like 0.5 heads?
Yeah, it just doesn't mean anything. There's no definition for it in this context.
So the probability only exists at those specific integer points. You can't have half a head.
That's the core idea. You can't have a partial outcome with discrete variables. It's this or that.
Very clear. Okay, so that's discrete. But what about when the possibilities aren't so neatly separated? What if the sample space is very big, as the source put it, covering all the small points?
Right. That's our transition into continuous random variables.
So continuous. Give us an example there.
Let's take the weight of college students. If you have, say, 1,000 students and you look at weights between 50 and 60 kilograms,
Okay.
you'll find students at lots of different weights within that range, maybe 51.2 kilograms, 55.75 kilograms,
Yeah.
Now, imagine you have a huge number of students, like 100,000 or even more. It starts to feel like it's covering practically every possible weight value in that range.
Ah, I see. It becomes like a smooth spectrum rather than distinct steps.
Exactly, a spectrum. Or think about property prices in a large city. The source mentioned plot rates.
Okay, how does that work?
Well, you wouldn't just see prices like 100,000, then 105,000, then 110,000, and nothing else, right?
Yeah, definitely not.
You could theoretically have a price of 100,000.57 or 101,234.99. Any value within a certain range is possible, down to the smallest fraction of a currency unit.
So it's not jumping between values, it's flowing through them.
Precisely. It reinforces that idea of continuous spectrum. So a continuous random variable, X, can basically take on any value within a given range. Infinitely many possibilities.
Okay, that distinction is critical. Discrete counts, continuous measures. But if they behave so differently, how do we talk about their probabilities mathematically? It can't be the same approach, can it?
No, it's fundamentally different, as you said. For those discrete variables, the countable ones,
Yeah.
we use what's called the probability mass function, often written as px. The mass idea sort of suggests the probability is concentrated at specific points.
Okay, PMF for discrete. And the math operation tied to that is?
Summation. because you're adding up the probabilities at each distinct point to find totals or averages.
Makes sense. Summing in masses. Okay, so what about the continuous ones, the spectrums?
Right, for continuous random variables, since you can't sum probabilities at infinite individual points.
Because the probability at any exact single point is actually 0.
Exactly. That's a key point. So instead, we use the probability density function, or PDF, often written fx. Density implies the probability is spread over a range.
PDF for continuous. And the operation isn't summation, it's
Integration. You integrate the density function over a certain range to find the probability of the variable falling within that range.
integration. Okay, so PMF uses summation for discrete. PDF uses integration for continuous. That's a massive difference in calculation.
It really is. And it carries through. Like, if you want to calculate the average value, the mean or expected value, EX,
You'd sum for discrete and integrate for continuous?
you got it. The underlying math tool matches the nature of the variable.
That's really helpful. And I guess each type has its own famous distributions that pop up a lot.
Oh, definitely. For discrete variables, you often run into things like the binomial distribution.
Like success-failure trials.
Exactly. Number of successes in a fixed number of trials. And the Poisson distribution.
Which is often about counts of events in a time period or space.
Yes, like
Yeah.
number of calls to a call center per hour. Lots of questions get asked based on those two.
Okay. And for continuous, what are the big names there?
For continuous, you'll frequently see the exponential distribution, often related to waiting times.
Mm.
The uniform distribution, where everything in a range is equally likely.
Yeah.
And the big one, the normal distribution.
The bell curve.
The bell curve, exactly. It's everywhere in nature and statistics. So many real-world phenomena approximate it. Lots of analysis, especially around the area property. Finding probabilities in ranges uses the normal distribution.
So normal is key for continuous. Okay, we have types, we have functions, PMF, PDF, we have common examples. But how do we describe the specific shape of a distribution's data beyond just its name?
Good question. That takes us into talking about descriptive measures. One important set is called moments.
Moments. Okay, what are they?
Moments are basically numerical characteristics that tell you about the shape and location of a distribution. Think of them as different kinds of averages or measures of spread and shape.
Are there different kinds of moments?
Yeah, the source mentions three main types. Moment about the mean, which tells you about the spread and shape relative to the average.
Mm-hmm.
Moment about the origin related to the raw values. And moment about any other point.
Okay. And how do these moments help describe the shape?
Well, they're the building blocks for other important concepts, like skewness and kurtosis.
Right, I've heard those terms. Skewness. That's about symmetry, isn't it?
Exactly. It tells us if the data is lopsided. Is it symmetric, like a perfect bell curve? Or does it have a longer tail on one side?
So it could be.
Right.
But what are the terms? Positively skewed.
Right. Positively skewed or right skewed means the tail stretches out to the right towards higher values. Think income data. Most people earn a moderate amount, but a few high earners pull the tail to the right.
Okay. And negatively skewed.
Negatively skewed or left skewed means the tail stretches to the left towards lower values. Maybe scores on a very easy test where most people do well, but a few score very low.
Got it. So skewness is about the lean or asymmetry. What about kurtosis then? That sounds more complex.
Kurtosis is about the tailedness or peakness compared to a normal distribution. Basically, how heavy are the tails and how sharp is the peak.
Okay. Tailedness and peakedness.
Yeah. There are three main terms you hear. Mesokurtic is like the normal distribution, average peak, average tails.
Meso for middle makes sense.
Then platykurtic. Think platypus or plateau. It's flatter than the normal distribution with thinner tails, less peaky, fewer extreme outliers.
Flatter, thinner tails. Okay.
And finally, leptokurtic. Think leaping. It's more peaked in the middle than the normal distribution, but it also has fatter, heavier tails.
More peaked and fatter tails. How does that work?
It means more data is clustered right around the mean, making the peak sharper, but there's also a higher chance of getting really extreme outliers compared to a normal distribution.
So stock market returns are sometimes described as leptokurtic. Big cluster around average returns, but also more frequent crashes or booms than a normal curve would predict.
That's a classic example, yes. It signals that extreme events might be more likely than you'd think if you just assumed normality. Kurtosis tells you about the outlier risk, essentially.
Wow, okay. So moments, skewness, kurtosis, they really add layers to describing what the data looks like.
They absolutely do. And the source also briefly mentions other properties people analyze, like variance, moment-generating functions, which are like mathematical formulas that encapsulate all the moments.
Kind of a master key for the distribution's properties.
Sort of, yeah. And things like PGF, probability-generating function, and characteristic functions, more advanced tools.
And of course, once you understand individual variables, you often want to see how they relate, which leads to
Correlation and regression. Yeah, looking at relationships between two or more variables. But like you said earlier.
That's a whole other deep dive for another day.
Indeed.
Right. Well, I think that brings us towards the end of this particular deep dive. We've gone from the basics of random variables, split them into discrete and continuous.
Talked about their distinct mathematical languages, PMF with summation, PDF with integration.
Touched on common distributions like binomial, Poisson, and especially the normal curve.
And then looked at how we describe their shapes using moments, skewness, and kurtosis.
Yeah, I feel like understanding these basics really is a shortcut. It helps you become, a more informed interpreter of data you see everywhere.
Absolutely. And that leads nicely into a final thought for you, our listener.
Okay.
Well, if we agree that knowledge is most valuable when you can actually understand it and apply it,
yeah,
how might recognizing these fundamental differences just between discrete and continuous variables, how might that sharpen your ability to critically evaluate data?
You mean like when you encounter economic reports or survey results or even just stats in a news headline?
Exactly. How does knowing whether they're talking about counts or measurements change how you make sense of it all? Something to think about.
A great question to ponder. Until our next deep dive, thanks for joining us.